So we are talking about the chapter 10 integers, and we have said that the question in this part is whether the prime factorization will always be unique. And to answer this, in other words, we say that given an integer n, one can write it as a product of primes in only one way, and that is the answer is yes. And that we call the fundamental theorem of arithmetic. We'll prove this theorem in the next part, but in this chapter we will build the machinery to use to prove this theorem, right? And then we are talking about the Euclidean algorithm. We have solved an example to show the number of steps and then procedure to like how we use the Euclidean algorithm. Now we will prove, now we will I'll give you the general version of the Euclidean algorithm. So what is Euclidean algorithm? It's a step-by-step method for calculating the common factors between two integers, all of two integers. So let me give you that. The question is, Euclidean algorithm. Let's say general version. Okay. So suppose we have two integers, right? And we need to calculate the highest common factor between them. And we do that by performing mindless steps as explained in the previous part of this chapter in the example. So that is, so first, divide A into B. I hope everyone understands the meaning of this phrase. A into B means divide B by A and then write B in terms of A, that how many times A plus something will be B, will be equal to B. And this is saying getting quotient Q1 and a remainder. So this is saying that getting a quotient Q1 and remainder R1. Okay. Then divide R1 into A. Okay. Into A, we will getting R2, getting remainder R2 less than R1. Then divide R2 into R1, getting remainder or 3 less than R2, and carry on like this until we eventually get a remainder 0. So carry on like this until we get remainder 0, which we must is all the r's are decreasing and are greater than or equal to 0. Now say the remainder is 0. When you get the remainder 0, so the remainder 0 occurs at n plus 1 steps. So let's say the remainder 0 occurs after n plus 1 steps. Okay. Then the equations representing these steps are, then the equations representing the steps are, it is going to be step 1 is going to be that we are writing B in terms of Q1A plus R1, and with the condition that 0 is less than or equal to R1 and R1 is less than A. Okay. Number 2 is A is written Q2 R1 plus R2 with the condition that 0 is less than or equal to R2. It is less than R1. Step 3 is R1 can be written as Q3 R2 plus R3. 0 is less than or equal to R3. It is less than or equal to R1. And by this, we carry on like this. We will go that n minus 1 into Rn minus 3 is equal to Qn minus 1 into Rn minus 2 plus Rn minus 1. And this will be 0 less than or equal to Rn minus 1 less than Rn minus 2. Then we have n into Rn minus 2 Qn Rn minus 1 plus Rn with the condition that 0 is less than or equal to Rn. It is less than Rn minus 1. And then n plus 1 is going to be Rn minus 1 Qn plus 1 Rn plus 0. And there we will end the general steps of, so these are the number of steps. So you can say step n minus 1, step n, and step n plus 1. Okay, this is the final step n plus 1. Perfect. And to present this, we'll give the theorem. (10.1). It's a golden one. So in the above, the highest common factor HCF of A comma B is equal to Rn the last non-zero divisor. So we are basically saying that HCF of A comma B is Rn, not equal to 0. Right. We can prove this theorem because we have already gave you the sketch and then we will prove it now. So let D is HCF of A comma B. We first show that we first show that the divides are power Rn by arguing from equation 1 on downwards. So we are talking about these equations in the proof. So by arguing from equation 1 downwards by proposition 10.2, the divides B minus Q1A and hence by 1 the divides are 1. Then by number 2 the divides are 2. By number 3 the divides are 3, and so on until by the step n or equation n the divides are n. Now we show that D is greater than or equal to Rn by working upwards. Upwards from equation n plus 1. So by equation n plus 1, we say that Rn divides Rn minus 1. By equation n, we say that Rn divides Rn minus 2. And hence by n minus 1, we say that Rn divides Rn minus 3, and so on until by 2 Rn divides A, and then by 1 we say that Rn divides B. Okay, thus Rn is HCF of A comma B, and D is greater than or equal to Rn. We conclude that D is Rn, and we have the proof is complete. Okay, so this is the proof of Euclidean algorithm by doing all these steps before. Otherwise, if you just have to write all of this in the theorem, and then it's gonna be a very long proof. Okay. Now, if we have this, we can talk about so many other propositions. So let's say we have a proposition and these are all consequences of this Euclidean algorithm. So we say if we have two integers and D is their HCF, then there are integers S and T such that S and T such that D can be written as SA plus TB. So you can further divide the highest common factor. Okay, perfect. And you can see this proof in the previous lecture series on the foundations of group theory. And we have already given you the example for the HCF. So now we will give you another proposition as a consequence. So that is proposition 10.4 says that if we have two integers, then any common factor of A and B also divides the common factor of then any common factor of A comma B also divides their combined common factor. That's a new thing. So if you have a common factor of A and then the common factor of B, so their separate common factors can also divide their combined common factor. So that's a new one. So let's say we can prove this because it's the interesting one. So let D is their combined, the common factor of A and B. Then by previous proposition 10.3 said that D can be further expressed. So by this, there are integers S and T, S comma T, such that it can be written as SA plus TB. Now, if M is a common factor of A and B, so does not need to be the highest common factor, but there can be any common factor. M can be any common factor of A and B. Then M divides SA plus TB by the proposition 10.2. And hence M divides D also. Perfect. We are now in a position to prove a highly significant fact about prime numbers. Namely, if a prime P divides the product AB of two integers, then P divides one of the factors A and B. So this is a very nice result, and we call it we'll put it into some proposition, but let's write this result in the golden words. So we say that if a prime P divides AB, where A comma B are integers, then P divides one of the factors of A and B. Okay. And for this, we have a proposition which says that now all these things are, sorry, we have a definition. Says that we have two integers and their highest common factor is 1. In other words, they are co-prime to each other. Yeah. So we say that this is the case between two integers. Then we say that A and B are co-prime to each other. Massive. Okay. So example can be 17 and 1024 are co-prime. Because HCF of 17 and 1024 is 1 only. So by proposition 10.3, by proposition 10.3, which said that if the HCF between A and B, and then if A and B are co-prime, then D is 1, then the 1 can be written as SA plus TB. That's something we are deducing by this definition in proposition 10.3. So we are saying if A comma B are co-prime to each other, that means their HCF of A comma B is 1, then there are integers S comma T such that 1 can be written as SA plus TB. Okay. And by using this fact, we can define another one, proposition 10.5, which says that we have two integers, or for two integers, we suppose A is, suppose C is an integer such that A comma C are co-prime to each other. So such that HCF of A comma C is 1, They're writing the consequences or like the mathematical definitions co-prime to each other, and C divides the product of A and B, then C also divides B. So this is the consequence of these three things. If we have two integers A and B, C is also an integer such that C is co-prime to A, and C is a common factor of the product AB, or C divides AB, then C also divides B because C was co-prime to A, so she should divide B. This is the consequence. Because there is no common factor between A and C, so if it is C divides the product, then it needs to be that C should divide B. Okay, part B. We suppose P is a prime number. A prime number is a number which has only two divisors, itself and one. And P divides the product AB, then either P divides A or P divides B. It can be from both cases. So this part B of this proposition will be crucial in our proof of uniqueness of prime factorization in the next chapter. And to apply it there, we need to generalize it slightly to the case of prime dividing a product of many factors as follows. So if we generalize this part B of this proposition, that will look like this. So we present that proposition as 10.6. We say that we have n integers, a1, a2 to n integers, and we say that P be a prime number. Okay. Then if P divides the product of all these n integers, then P divides some of AI's, some of the numbers of those n integers for some I. And this can be proven. It's an interesting one, so I'll prove it. This will be, and then we will end this chapter. So we prove this by induction, and we say that we prove by induction. We say that let P of n be the statement of the proposition okay. So first we say P of 1 says that P divides A1, then if P divides A1, then P divides A1, which is trivially true. Now suppose P of n is true, which means let we have n plus 1 integers with the condition that P divides their product. Right? We need to show that P divide some of them for some I. We need to show that P divide some of them for some I. Okay? And to show that, let's do that regardless the integers as a product AB where we say that where A is the product of first in n integers and B is the nth integer, n plus first integer. Okay? Then P divides A, B. So by proposition 10.5b, either P divides A or P divides B. Now we have two cases. If P divides A, that is saying that is to say that P divides A1, A2 up to AN. Let's put it in the line. Okay. Then by P of n, we have that P divides some AI for some I, because we have assumed that P of n is true. Now, if P divides B, then P divides the nth, n plus first integer. Thus, in either case, P divides one of the factors A1, A2, AN plus 1. So we have established that P of n implies P of n plus 1 Hence, by induction, P of n is true for all, and this is a proof of our proposition. Right. Thank you so much. Please do subscribe and give the comments if you need any improvement in the lecture series. Bye. Thank you.